Hello, welcome to this video on lesson 1.2, functions, inverses, graphing, adjustments. And in this video, we're going to talk about the first portion, mainly just the functions, what makes a function, and then kind of identifying the domain and range of those functions with a little bit of composition thrown in. This is going to be the first of 3 videos for this lesson, so they should be hopefully relatively short. Okay, so the first thing that I want to talk about with functions is some definitions. So we can see here a relation is just any set of ordered pairs. Okay, and so you could see this with ordered pairs or a graph or a table. What makes a relation a function is that y is a function of x, and the main way that we can tell if this is true is that for each x value there is only one y value. Okay, and that's very, very important. An even easier way to tell this, like visually, is with the vertical line test, the VLT, not the BLT, the VLT. Okay, and then domain and range, you guys know, right? Domain, these are your x values. Range is the y values. So what we're going to do first is we're given in the examples here some equations and some graphs, and we want to determine, is this a function of x? So the first example we have here is x plus y equals 1. And easily to kind of look at this, it's easiest if it's in slope-intercept form. So I'll rewrite this as y equals negative x plus 1. This is a linear function, a straight line, okay? And visually, if you would see this, right, this is a slope of negative 1 with a vertical shift up 1, so something like this, right? So yes, this is a function. Okay, it would pass the vertical line test. Whereas example 2, right? In vertical line test, I mean, you just draw a vertical line straight down, right? And if it intersects at more than one spot, not a function. For example number 2, if I draw a vertical line straight down, notice that it intersects in 2 locations, right? So for one x value, there's 2 outputs. There's 2 y values. Okay, so this is not a function. No. Okay, number 3. Here we have y is equal to negative x squared plus 2. Remember that quadratics, these are parabolas, right? This is a downward facing parabola shifted up 1. So visually it would look like this. And if we drew a vertical line, notice you're only going to have one intersection point. So yes, this is a function. Okay, we'll move on to number 4. And notice number 4 here, again, we want to solve for y. So if I solve for y, we have y squared is equal to negative x plus 1. And then we'll take the square root, which we know gives us plus or minus radical negative x plus 1. Okay, and if I take this a step further and I factor out the x on the interior here, we get plus or minus the square root of negative x minus 1. Okay, so visually this is a sidewards facing parabola shifted over 1, right? And we have horizontal reflection. Okay, so notice in this example, right, this is not going to pass the vertical line test. And maybe you're saying, hey, I can't translate equations to graphs that easily. What's another indicator? And I would say here, the y squared. And notice that in example 2, we have a y squared. What this produces is it produces 2 x values for one y value. Okay, and you can see the plus or minus here. Okay, so that's what makes this not a function, right? And if I was to solve number 2 here for y, we'd have to take the square root on both sides to give us just a positive y, and that produces a positive and negative x value, okay? All right, so that is functions. The next thing that we want to talk about is how do we evaluate functions, and with that we get some composition. So we're going to identify two functions. We'll identify f of x equals 3x minus 1 and g of x, which is x squared. And they want us to find the following. So f of 10, I'm going to take my f function, okay, and all I'm going to do is plug in 10 for any x. So 3 times 10 minus 1. And remember, again, in calculus, right there, that is a numerical answer. You can stop. You do not have to simplify. That could be your answer. But if we simplified, right, this would be 30 minus 1, which is 29. For number 6, it says g of x plus delta x. Now, this is weird, but again, whatever's in this portion here, right, what we did with this one, you just plug it in for wherever there's x. So this becomes equals x plus delta x quantity squared, okay? And that's it. If you wanted to evaluate this, remember this is x plus delta x times x plus delta x, and you can FOIL this out, calculate this, which would give you x squared plus 2x delta x, right? And delta x is just another term. I know that looks kind of weird. Plus delta x squared. Okay, so that is evaluating functions. Now we're going to get into composition, which should be reviewed. We talked about this in Accelerated Math 3. And function notation or composition notation is just placing one function inside of another. So here where it says g of f of x, I'm going to take my g of x function and I'm going to plug in f of x wherever there is an x. So I'm going to take the 3x minus 1 and I'm just going to plug it in. So this becomes g of 3x minus 1, which if we evaluate this gives us 3x minus 1 squared. Okay, and that is it. Over here, fog, this is also composition notation, right? Functions embedded within each other. And we can just rewrite this as f of g of x. It's the same thing, just written a little different, okay? So I'm going to take my g of x function, which is x squared, and I'm going to plug that in. So f of x squared, don't forget my equal signs, which gives us 3x squared minus 1, right? I just plugged in g of x into my x here, okay? And that would be your answer. Okay, next, domain and range. Determine the domain and range for each function. Remember, domain is your x values and range is your y values. So for number 9 here, you got to think about with square root functions, okay, what are our restrictions, right? And in our radicand here, this has to be greater than or equal to 0. I can't have negatives, which will produce imaginary values. So what we do is I'm going to take my radicand, x minus 1, set it greater than or equal to 0, and solve. Okay, x has to be greater than or equal to positive 1. So that is my domain. X is greater than or equal to 1. And written as interval notation, it would be 1 to positive infinity. Okay, the range, you almost have to think about this visually. If I was to draw this, if I shift over 1 and I draw my square root function, okay, notice that the range includes 0 and it goes all the way up to positive infinity. Okay, so that is your range. And you could also say y greater than or equal to 0. That would be inequality notation. For number 10, number 10 is a rational function, right? And rational functions, aka fractions, we have to worry about the denominator not being 0, right? Denominator cannot equal 0. So I take x minus 2, I set it equal to 0, and solve, and I say, hey, x cannot be this, right? So that's your domain. Your x values cannot be equal to 2, so we would say x has to be greater than 2 or less than 2. Okay, and then written as interval notation, that would be negative infinity to 2. Parentheses on both, because I can't include 2, right? We can't have 2 be a part of our domain. Okay, and visually what's going on here is we have an asymptote at 2, right? I can't include that value. So we get a rational function which looks like this. Okay, and range-wise, that would be that y cannot be 0. We have a horizontal asymptote at y equals 0. So we would say negative infinity to 0, union 0 to infinity. Okay. And number 11, we have a visual example. Sometimes these are easier. Notice that here for this example we have an asymptote here at 0 and an asymptote at 2. So x cannot be those values, right? So what we're going to say is negative infinity to 0, union 0 to 2, union 2 to infinity. Okay, that is the domain. I have breaks, right? I don't have an x value here. I don't have an x value here for my graph. Okay, range would be the y values. So notice that we have kind of an asymptote, a break here at 0. So negative infinity to 0. And notice that our next y value starts here at 1. So union 1 to infinity. Positive, you can write positive if you want. If I don't see a negative, I'm going to assume it's a positive infinity. You don't have to put positive. But yeah, okay. So notice I tend to like interval notation more. There are certain times I'll use interval notation, certain times I'll use inequality. Both are fine unless the problem specifically asks for one or the other. Okay. So in this video, we talked about functions. We said, is this a function? Yes or no. And we also talked about the evaluating functions here with composition and the domain and the range.